Consider a triangle and its symmetries. This includes reflections and rotations. These reflections and rotations form a group. A group is a set of elements together with a binary operation that satisfy the properties of closure, associativity, the identity element, and the inverse element. G is the group of quotients excluding the number 1 over 32, and the binary operation is a plus b minus 32ab. I'll start by proving the group is closed. To show this, all I need to do is show that C is in the group, and for it to be in the group, it needs to be a quotient that isn't 1 over 32. This process also proves that it's a binary operation. To be associative, the left-hand side must equal the right-hand side. And to find the identity element, I need to find the element that does nothing to A. Here, it's 0. The inverse element is the one that when applied to A returns 0. Here, it's A over 32A minus 1. The Latin square property states that if G is a group and X and Y are elements of G, there exists a unique element G in G such that XG equals GX equals Y. The Cayley table represents this. This is the table for D3, the group containing all symmetries on an equilateral triangle. Every row and column contain each group element once. Notice the table is not symmetrical. This means it's not abelian. A subset of GH forms a subgroup if H also forms a group under the same binary operation following the group axioms. The trivial subgroup is the group containing just the identity element. Recall the group of reflections and rotations on an equilateral triangle. The dihedral group is the group of symmetries of a regular polygon. A polygon with n sides has two n symmetries, n reflections and n rotations. We can represent the elements of Dn as matrices, with composition being matrix multiplication. The symmetric group is a group of all permutations on n symbols. Every permutation is expressible as a product of disjoint cycles. There are n factorial ways to permute a set with n elements. An alternating group is a group of even permutations on a set of length n. It is the normal subgroup of the symmetric group. The order of the group is n factorial over 2, and the group is abelian if n is less than or equal to 3. Consider an element x from G. To form the smallest subgroup containing x under group multiplication, we would need an identity element, the inverse of x, as well as all powers including inverses of x, for it to be closed. For group addition, the group would need the identity element as well as all positive and negative multiples of x. These are restatements of the definition of a subgroup. The definition states that the subset must form a group on its own, so the subset of G contains the identity, the inverses, and is closed. If H is a subset of G that fulfills the conditions given, then it's non-empty, and the group product for H is the same as the group product for G. To show H is a group, I just need to prove it satisfies the four group axioms. I need to show that if x and y are elements in H, then xy is in H. If the inverse of y is in H and we let A equal x and B equal the inverse of y, we know A times the inverse of B is in H, and then x times the inverse of y is in H, so xy is in H. As G is associative, H is 2. Let E be the identity of G. As H is non-empty, let x be an element in H. If A equals x and B equals x, then A times the inverse of B equals x times the inverse of x, which equals E, so the identity element is in H. If A equals E and B equals x, then A times the inverse of B equals E times the inverse of x, which equals the inverse of x. So every element in H has an inverse in H. As H satisfies the group axioms, it's a group, and it's therefore a subgroup of G. If H is a subset of G, then it is a subgroup if it's non-empty, closed, and closed under inverses. We can check the 4 group axioms. We've assumed it's closed by the definition given. As G is associative, H is too. This is the same as the one-step proof, and it's closed under inverses by the definition. It's therefore a group. I'll be applying the two-step subgroup test. As the determinant of every element in the special linear group is non-zero, they are invertible. The identity element for any n by n matrix has determinant 1. So the identity element is in the special linear group and it's non-empty. Now to show it's closed, we must show that given any 2 elements in the special linear group, the product is also in the group. Using the two-step subgroup test, all elements of S are elements of D4. It's therefore a subset. S is non-empty as it has elements in it including the identity element, and it's closed under the operation multiplication. S is also closed under inverses. This means S is a subgroup of D4. Remember that when using a Cayley table, the entry at the start of the row is the first to be considered, and the entry along the column comes next. In cases where the binary operation is commutative or abelian, this doesn't matter. To show that S is closed under inverses, we just need to find them. Checking each element in the group has inverse by setting them equal to the identity and finding the inverses. S is therefore a subgroup of D4 as it's non-empty and closed under the operation and inverses. If H is a subgroup of G and I were to multiply all elements of H by some element of G, then the set of products is a coset. The easiest way to understand cosets is through examples. We're asked here to list all distinct left cosets of H in A4. To start with, we can use Lagrange's theorem. There are 12 elements in this group and 4 in H. 12 divided by 4 is 3, so there are 3 left cosets. One of these is H itself, so there are just 2 left to find. I'm going to pick something in A4 that's not in H. 1, 2, 3 will do. I'm going to multiply that by each element of H. I'm also going to choose 1, 2, 4 and do the same. And these are the 3 left cosets. The direct product of 2 groups is the operation that takes 2 groups, G1 and G2, and constructs a new group. It's the set of all groups where the first component is from G1 and the second is from G2. The notation is the same as the Cartesian product of 2 sets. This example involves cyclic groups. From the greatest common divisor, we know that for some a and b, am plus bk equals 1. This means g equals gam plus gbk. And so gam is an element of gk and gbk is an element of gm. And so the direct product of gk and gm is g. This is a map between 2 groups where the group operation is preserved. This means that the group homomorphism maps the identity element in G to the identity element in H. The inverse map is also preserved. The kernel of the homomorphism is the set of elements of G that are mapped to the identity of H. The image of the homomorphism is the subset of elements of H to which at least one element of G is mapped by F. The kernel is a normal subgroup of G and the image is a subgroup of H. The very basic definition of a group isomorphism is that it shows that two groups are the same except for the names of the elements and the name of the binary operation. There are a few theories relating to isomorphism that are worth remembering, as they make proof really easy to understand. To start with, the easiest thing to do is to find the identity element of both groups. It's clear the identity element of G is 0, and in H it's B. I can also see that the tables are symmetric, so both groups are abelian. Now I need to find what 1 and 2 map to in H. There are only two options, so I'm going to try mapping 1 to A and 2 to C. I need to check that the function 1 add 2 maps to A and C as well, and the group is therefore isomorphic. And that's the end of my very basic introduction to group theory.